So if we can go to page 10 in your packet, we're going to finish up quiz review worksheet 1. That's it. So we'll finish up quiz review worksheet 1, and then we'll start worksheet 2. We did synthetic division. We did good practices yesterday. We'll do another one today. Let's start with number 9 here. So number 9 on page 10. Okay, so take a look at number 9. Let's go down our checklist. Expansion power rule should be our first option, but really, we already see there's too many terms in the denominator, right? We're not going to get, we're not going to make a whole lot of progress by expanding that denominator. So expansion power rule alone is out of the question for now. Our second option is U substitution, right? What's our potential U value? Yeah, parentheses, okay? Let's just target the parentheses. If we let it be the entire denominator, we're going to have a chain rule, which is going to produce a little too much for our derivative to handle. So, or for our match to occur. Okay, so let's target just the parentheses for now. I'm going to rewrite the problem so we can kind of. I like to have the dx sitting out to the right, so kind of have a little bit of separation, but it's really not that important, just visually to make it match everything else that we've been doing. Okay, 1 over u squared times du over 2. That's the result after I replaced what I underlined. I can push the 1/2 out in front. Okay, I want to pause for a moment here. I want to make sure that we can see the problem that we have in front of us. It cleans up nicely. This matches one of the rules that we can apply. But my question is, which rule is this going to be the best fit for? Not, it's going to be power rule. Okay, so a to the u would be like a constant raised to a variable. But here, this is a variable raised to a constant. So there's 2 options, right? It's either power rule or it's natural log. Power rule is correct. Why is this not natural log? Squared, right? So it's anything in the denominator doesn't mean that it's just going to be a natural log rule. I think that's our natural tendency because we see so many u variable in the denominator that our natural instinct is just to attempt natural log. But I want to keep reminding us that you always want to look at the exponent, right? If that exponent is anything other than 1 in the denominator, you got to bring it up and go through power rule, right? The natural log rule is think of it as the exception to power rule. There's one instance that you do natural log, everything else you do power rule. Okay, so you got to bring that u up to the top. And now you can do power rule. Okay. Add 1 to the exponent, divided by that new exponent. I'll bring the u back down to the denominator. And then I also want to bring back my original variable. Okay, I want to keep reminding us of this, especially when you're going through U substitution. I haven't handed back your first chapter 4 test yet, but the minor mistake that I see a lot of students make is students go through the whole process of U substitution, which is fine, but then in the end, they forget to bring the original variable back. And because of that, you're just losing these unnecessary points. So just remember that when you go through U substitution, you really need to understand that the U is only a temporary variable, right? You should never present your answer in terms of U. But for indefinite integrals, right? For definite integrals, then we should just get numeric values at the end. But if it's an indefinite integral, and if you're going through U substitution, you got to bring your original variable back. Don't present your answer in terms of U. Yes. Oh, why not the natural log rule?
No, I mean, like, why wouldn't it be 1/3?
Oh,
Yeah, after that, like, wouldn't you usually like add 1?
we do, right? What's -2 plus 1?
Oh.
-1. Yeah, I know it's easy because everything is backwards with negative numbers, right? So we just really want to take the time to add 1 because everything is backwards with negatives. Okay. Good. Any other questions with 9? Okay, number 10. 5 to the secant x, tangent x dx. Another reminder I want to keep making is that even if you see rules that looks like you can apply, we can't separate problems if multiplication is involved, right? We really need to think of this as one messy problem. And because it's so messy, we're going to have to go through U substitution, okay? We don't have a rule that can handle what we see in front of us. Even if you're looking at this saying, okay, I got a rule for secant tangent, I got a rule for 5 secant, I can just separate them and handle them separately. That's everything. When things are connected by multiplication, we're not going to be able to separate the problems like we would prefer to. So we got to go through U substitution for number 10. What could be our U value for 10? Yeah, that exponent, right? And if we can let that exponent be secant, then we're essentially targeting a to the U. Now, this is a to the U. Okay, a to the U is when you have a constant, like a 2, 3, or 5, or 7, raised to an exponent that's a variable. All right, so seeing that secant tangent is encouraging because we know that secant's derivative is secant tangent, so we should be able to get that secant tangent to nicely pair up and drop out after we go through our U substitution process. So we should be able to look at the problem and see that this lines up nicely with our a to the U rule. So now we find our a to the U rule, which is 1 over natural log of a times a to the U. So it's really the original problem showing up, just a little bit of extra coefficient that needs to occur because it's not base e. You can rearrange your final answer any way you like. You can have it under one fraction. You can separate them. Okay. Okay, take a look at 11. How would you start number 11? U substitution. What's our U value? The exponent, yeah, the full exponent, okay. Yeah, anytime you're targeting the exponent as your potential U value, you're really not going to be able to pick and choose with the exponent. So If it's going to be the exponent, it's going to be the entire exponent. Okay. Another thing to remind us is that the bounds, there are bounds in this antiderivative, but we don't touch that, right? That's not until the very, very end of the problem. We really want to treat this like as if we don't see the bounds at all initially. Sorry. Okay, we'll target the exponent as our U value. X's goes away, but careful, there's a -1 that's still remaining. Yeah, the -1 came from the -1/2 x squared, so we have to just keep track of that -1 all the way to the end. Okay, so integral of -e to the u, we know e to the u is just e to the u, so we know our antiderivative is just e to the u. Now, once you're here, normally you would have a plus c, right? We don't involve the plus c because we have bounds involved. Okay, you have two options here. The first option is you can bring your x back into your answer. So bring the -1/2 x squared and then work in the 0 and √2, which many of you guys prefer, which is fine. The other option is converting the bounds, such as 0 and √2, in terms of u, and then just use the bounds in terms of u, and then use this antiderivative in terms of u. That second option. That's what I'm going to present so that we don't forget about that process. But what we don't want to do is this. We don't want to involve the 0 and √2 with the u, because then you're mismatching variables, right? The 0 and √2 is in terms of x, that's in terms of u. We can't plug something that's x in for u. Okay, so we don't want to take that step. Okay. So either one of the first two options is fine. I'm just going to go ahead and show the converting the bounds method. So if my lower bound is x equals 0, I can push it through that relationship there. So that means u is equal to -1/2 0 squared, which is 0. So my lower bound has been adapted, but it ends up still being 0. If my upper bound is √2, I push it through that formula. I get u equals -1/2 √2 squared, which is -1. -e to the u is my antiderivative in terms of u. My lower bound starts as 0 and ends as 0. My upper bound starts at √2, it ends at -1. Okay. Just keep in mind that whatever you start as your upper bound is going to remain as your upper bound, even if it suddenly changes order. Okay, the order, the numbers, the upper and lower bound being out of order is not a big deal. Okay, it's only a big deal if you're trying to read the graph, you're trying to push something onto a graph, you're trying to read the graph from left to right and deciding, wait, is this region positive or negative? But if it's part of a definite integral process, I don't really care. I just going to just apply the upper bound where it is. Now, if you want to flip the bounds, you can. It just takes an additional step, and you got to change the sign if you do that, which is fine. But just understand that it's not wrong if you evaluate the bounds out of order. Yes. Yes. You can replace the u in terms of x and then use the original bounds.
So it would be like -e to like -1/2
But not plus c though.
Oh, right.
You how you involve 0 and root 2.
Yeah.
But yes, you should get the same answer as me. And the second problem, number 12, I'll work it out with that method that you mentioned. But I do want to keep reminding us of this method, even though I'm not going to ask you to show this method. I'm not going to say, hey, do this problem using this method. But I don't want us to forget about this method because this does show up in some form or another on the AP exam, on the multiple choice, for instance. Okay, upper bound first, minus, then the lower bound. I want to keep reminding us that anytime you see 0, just be careful of 0. I know that the tendency is when you see 0, you just automatically assume that it's going to wipe everything out, but it does happen a lot, but it doesn't happen every time. So take the time and make sure that 0 doesn't completely wipe everything out. In this case, what's e to the 0? 1, so it doesn't wipe it out. Okay, so just because you see 0 doesn't mean that it completely goes away. Take the time to convince yourself of that. So -1 over e is the result here. I have two negatives, which becomes positive. It's a +1. So either method you go through, you should get the same value as what I did. Okay, try number 12, same process. It's a way to kind of practice through the U substitution definite integral process. So try number 12. Oh, yes, this is still U substitution, but here you can decide if you want to convert the bounds later or not. You don't have to. But I'm going to show the other method just so that you can see the two methods involved. But you can choose either one. But still U substitution, right? We still got to go through the full process. We still ignore the bounds until the time is right. Okay, just a coincidence that the answer ends up being the same. Okay. Either case, we let the U value be 3 minus x, derivative is -1. So after we make our substitutions, we're just left with negative integral e to the u, which is just negative e to the u. But here I just decided that I want to go through my other method. So I'll bring my original variable back, which is 3 minus x. And then I can use my original bounds because now I have a match in terms of variables. So upper bound first, 3 minus 4 is -1 minus, and then plug in my lower bound, which is 0. 0 is 1. So, okay, it's just a coincidence that these are the same answers, okay? But it's a completely different problem. Okay, try number 13. 13 is a way to practice recalling the new integral rules. So if you look at 13, all the trig functions are the new ones that involve natural log. So see if you can recall those rules. We can go over them as well. Okay, is anybody still looking at number 12? Okay, so these are the 4 new trig rules that involve natural log. The way I go about remembering these rules is I think of tangent as sine over cosine. And the way you can derive it is you go through this process and go through U substitution. And I always target that denominator. So I know that it's the denominator that's going to show up in my natural log for my tangent rule. Okay. And then also cosine produces a negative sign with U substitution. So because of that, there's a negative that's going to be involved in the antiderivative for tangent. So the first one is going to be negative natural log absolute value of cosine of x. Secant also involves natural log. The rule kind of looks like involves the trig functions that you would expect from secant. Secant derivative of secant tangent, so that shows up again, but it has this particular form of the trig functions being added together within natural log. Cotangent kind of resembles tangent. It's the reciprocal of tangent, so cotangent, I could think of it as cosine over sine. And that's how I remember that I know it's the denominator that's going to show up in my natural log rule. Sine's derivative is a positive cosine, so that's why cotangent ends up giving me a positive natural log. And then finally, cosecant has a similar format as secant. It has natural log. It has two trig functions added together. But cosecant is going to be cosecant plus cotangent. Mm-hmm. Okay, 14. Take a look at 14. How would you start this problem here? This is too complex for one rule to handle. So what's our U value? The entire exponent. Yeah, the entire exponent. We want that 3 involved. That exponent 3 is good because we know the derivative is going to bring down to squared, and that should handle this messiness that we have in front. So targeting a U value that has a higher degree than the remaining x's is a good start. So, and also we see that this is going to head towards a to the U, right? This will hopefully turn into a base 7 exponential function, base 7 rule that we can use. Okay, there's a little bit of a chain rule here. So outside function is parentheses cubed. Inside function is the 5 minus 2x. Okay, outside's derivative. We get 3 parentheses squared. Inside's derivative, what remains for inside's derivative is just -2. And then you copy that 5 minus 2x back down. Okay, cross multiply so that you can eventually get that dx by itself. Okay, we make our substitution. Five minus 2x squared goes away like we want, but there's a leftover what? It's good, -1/6, right? -1/6 in the denominator. So you should be able to recognize this as a to the U rule. and then finish it off from here. Okay, let's go to quiz review worksheet 2. And at the top, see if you can recall the new integral rules just to get that practice in. So top of page 11. Okay, is anybody still looking at 14? Okay. And while you guys are doing this, also, I want you guys to change number 2 as well. Number 2, we're just going to do x plus 2 in the denominator. So I'm not going to have long division on the quiz. You can solve using synthetic division. I think that's what we prefer if we can. So.
What are all the things you have to know?
In terms of rules, or?
Yeah, like rules.
Yeah, so rules, I would say the rules you see have in front of you, and also your original trig integrals and derivatives. So these rules here, and then if you look on page 7, yeah. Because if you know these trig derivatives, you know how to involve the trig integrals, right? So.
You have to memorize like the L and U.
Yeah, this one we should know. E to the u is e to the u times u prime. Natural log of u, that's u prime over u. We don't have to worry about this one here. This one is the undoing of a to the u, so I think it's good to know this one too. Yeah.
Are all the natural log rules absolute value?
Only these 4. Right, only tangent, cotangent, secant, cosecant. These are the only ones that have natural log involved. All the other integral rules are just coming from the derivative rules.
Yeah. But like 1 over u, integral of 1 over u, that's absolute value of u.
That's absolute value. That's the natural log absolute value of u plus 2. Yeah, we gotta know this one. Yeah, this one we've been going through from 5.2 and 5.4, and this is 5.5. Yeah, so page 7, those are good rules too. Good page to practice and make sure you know all your rules. Okay, so page 11, let's try number 1. Okay, how would you start this problem here? Yeah, U substitution. Too many terms in the denominator. Okay, where's the U value? Good, parentheses, right? Target the parentheses. Parentheses is not always going to be where your U value is, but if it's there, at least explore that possibility, right? We don't want to overthink a problem, especially if the parentheses is there for us to at least explore that option. I like to push the dx out to the right just so that it can look more like my setup for other problems. You don't have to, it just makes everything more familiar in terms of where they are located. Okay, we're saving that x to the 2/3 for the derivative to pair and match up.
Mr. Yang, couldn't you just distribute that and then be powerful?
You mean for number 1?
Yeah, number 1.
If I distribute this through, I'm left with multiple terms in the denominator. And if I bring it up, I'm really not going to be able to make much progress. If you,
Oh, okay.
yeah, I mean, I would do it if this was in the numerator, but the denominator, it just makes it really ugly, and I can't, with the plus sign in between, I'm not going to be able to make much progress algebraically. So, yeah, so anytime there's multiple terms separated by addition or subtraction in the denominator, I'm almost automatically just thinking, okay, expansion is not going to be easy here. Okay, so okay, make your substitution. You should be able to get the x's to line up nicely, numerator, denominator, but there is a leftover 3 that's going to have to be part of our answer here. But once that 3 comes out, it should look like an easy rule for us to apply. 1 over u, that's natural log, right? Okay, number 2, you're changing that problem in that denominator to be just x to the first power. Okay, any questions with 1? Okay, number 2, if we go through our full checklist here, expansion is not possible, too many terms in the denominator. If it was just one term, then we can separate, but there's too many terms. Second option, U substitution, is not going to be a good fit, whether numerator or denominator. So this is going to be a long division synthetic division problem. Long division synthetic division has a very specific look to it. It has this rational function, multiple terms, numerator and denominator, and the degree of the numerator is higher than the denominator. So it has that specific look to it that kind of tells you that it's going to be a long division of synthetic. This can be handled by either long division or synthetic, but because the degree is to the first power in the denominator, we prefer synthetic division. Is a little bit faster, a little less cumbersome. So let's go through this process of synthetic division here. We always pull the opposite sign that we see, and then half box. Next up, we're going to list out the coefficients in front of the variable. So no variables is going to be in our diagram here, just the coefficients. So we start off with 1, because 1 represents x to the 4th. But what comes next? Good. Why? Yeah. So every column, every imaginary column that you see is going to have to represent every degree that comes after degree 4. So we need a degree 3. There is no degree 3 here, so we need to have a placeholder for 0 that represents x cubed. Okay, we have no x squared either, so we need a placeholder 0 to represent x squared. We do have a coefficient. We have x to the first power, linear term, which has a coefficient of 1, and then the constant, which is -4. So we do need to set it up this way, especially if there's a missing degree that's hiding between the terms. Okay, so here are the steps. We always drag the first number below the line. As soon as the number shows up below the line, you're ready to multiply with this outside divisor here. So -2 times 1 is -2. Okay, add. Once it's below the line, it's ready to multiply again. -2 times -2 is 4. Add again. 4 times -2 is -8. Add. -7 times -2 is 14. Add. So if there's a number other than 0 that shows up at the end, you know you're staring at a remainder.
We always get a remainder.
Most likely, yeah. So we also now have to assign the new degrees for these coefficients. So we start off with x to the 4th, but we're going to now have what? X to the 3rd. Okay, because we're dividing by x to the 1st power, so every degree is going to fall by 1. So the first term will be x cubed. Now every term is just going to decrease by 1 degree. So next up will be x squared. Linear, constant, and the last term is going to be divided by x plus 2. So the remainder is indicating that I can't divide any further. So 10 over x plus 2 is as far as I can get. Now keep in mind, this is not the answer, okay? We haven't done anything calculus related. We just rewritten the problem so that the calculus can be more manageable. Because every term now is going to be ready for power rule. Except for that last term, because that last term is just going to be set up for an easy U substitution natural log rule. So power rule, power rule, power rule, power rule, and this is U substitution. That's going to be set up nicely with natural log. Okay, if you want to go through a full U substitution process, you can. But if you just understand that x plus 2 is just going to be the U value and there's nothing left over, you can jump directly to setting it up and involving natural log. Okay, so let's go through power rule for most of the terms here. Okay, what does 7 turn into? Yeah, that's right. Every degree rises by 1. Okay. You can reduce the fractions if you like. You can push the coefficients out as 1/4 and 2/3 if you like. But any variation of this answer is fine. Okay, any questions with 2? Okay, take a look at 3. Any suggestions as to how to start number 3? Okay, U substitution. What's our U value? Denominator, yeah, denominator. So as soon as I recognize it being a U substitution problem, I'm looking for 2 places. I'm either looking for parentheses or I'm looking for denominator. So those are the most common places where the U value shows up. But sometimes we kind of have to pick and choose and kind of piece the puzzle together here. But here, pretty easy to spot, I think. Okay, matches nicely with our natural log rule. This is u to the first power in the denominator. Okay, questions with 3. Okay, take a look at 4. How would you begin this problem?
I all the terms.
Okay.
Split it up.
Good, yeah, split up. Okay, so there's only one term in the denominator. You really want to split up. You really want to treat this like 3 separate problems, okay? So no U substitution, well, at least not initially. We really want to kind of think of it as, okay, I would rather handle this as 3 separate problems than one messy problem. So we can do that if there's only one term in the denominator. Okay. And then once we have everything separated, then we can handle each individually and apply the appropriate rule, because now we have the flexibility to do everything independent of each other, right? We couldn't do it before because of division, but now we should be able to get it cleaned up. Okay, so how do I clean up this first term here? Okay, good. So you can either bring it up and then add exponents, or you can, or if you divide bases, you can also think of it as subtracting exponents, right? So either 2x plus negative x or 2x minus 1x, either way, you're left with just e to the x. Second term, we can just imagine the e to the x just canceling out, so I'm just left with plus 2. Now the third term. Good, right? We don't have a rule for 1 over e to the x, but we do have a rule for e to the u in the numerator. So we really want to push up to the numerator. Now, you don't have to write it out this way, but I just want to help remind us that there's a little bit of U substitution going on here. We got to keep track of the fact that there's a little bit of leftover from this process. Okay. So e to the x just becomes e to the x. 2 becomes what? 2x, get 2x. And this is a little bit of U substitution. E to the negative x remains e to the negative x, but there's a little bit of extra negative 1 in front, right? If I have an easy U value, my leftover is predictable. It's always just going to be the reciprocal of the derivative. So negative x becomes negative 1. You flip negative 1, it's still negative 1. You can go through the full U substitution process, but if you can recognize what that pattern is, you can just pull that out without having to go through that additional step. But if you want to write out the steps to convince yourself, you're more than welcome to. But your exponential function will remain the same, just a little bit of extra leftover that we have to keep track of. Okay, back page whenever you're ready. Okay, for the remaining problems, I just want us to identify the first step, right? You can get that first step down. That will make things a lot easier if we can go down the right path. Okay, so take a look at number 5 on page 12. And how would you start this problem out? Ignore the bounds, right? We're not going to touch the bounds until later. Okay, any ideas? U substitution. Okay, what's our U value? The exponent, the 3 over x. It doesn't seem like this 3 over x is going to do a whole lot of good handling the x squared here, but that x is in the denominator, so things will behave in ways that we may not expect. So if our U value is 3 over x, how would you get this ready for us to find the derivative? Yeah. If you leave it like this, you got to go through quotient rule, right? We prefer not to go through quotient rule, so we can write it as 3x to the negative 1. And now derivative, right? Bring the exponent down, subtract 1 from the exponent. and you see that x squared pop up, and that is what's going to handle that x squared that we want to go away. Okay, so you guys can finish that problem a little bit later. Let's don't worry about number 6. Number 6 is kind of a change of variable problem, which I won't put on the quiz. Okay, number 7. How would you start number 7? U substitution. What's the u value? Parentheses. What's another way to write x over 2? 1/2 x. I think we prefer that. You don't have to, but I know we prefer that form. It's a little bit less confusing. Okay, number 8. Take a look at number 8. How would you start number 8? Yeah, U substitution. What's our u value? It's a little too small. Exponent, you're left with 4 to the u over 1 minus 4 to the u. That's too messy of anything to denominator. Yeah. So it does take someone to take a little bit of guess and check to kind of get there. Okay, as a reminder, the derivative for a to the u is natural log of a times a to the u times u prime. Looks a lot like e to the u, just a little bit of extra in front. Okay. All right. 9 is a little tricky here. Any thoughts? The denominator is a little too much. The a to the u is going to leave us with more things than the cosine can handle. Okay, that's part of it. But if you let the u value be sine of x, what rule are you trying to work towards? What rule do we want to eventually have this turn into? A to the u. Now, look at a to the u. Where's that a located? Numerator. So this is a little out of place. We really need to rewrite this problem before we can decide. Yeah, so this is a little tricky. You got to get that 2 up to the top. Get that foundation set before you can get that u value to be correct. So this is a little tricky here. So now your u value is negative sine x, and that now things will work out cleanly. Okay, you guys have keys attached for worksheet 1 and worksheet 2. I know I didn't work through all the problems, but I just want to get that first step down, and you guys can practice the rest of it. I have the morning review attached as well, along with the key. Tomorrow I'll have a morning review at 7:30. I'll send out a reminder, no calculator. Okay. Review your rules on page 7. Page 7 has all the rules that you need. So we're going to kind of build up our formula vocabulary to okay.
Number 12. So you did the 30 pounds for 11, and then I tried to do it for 12. But then it gave me the -1 on the top. So when you switch it, don't you have to put it negative?
You can, yeah. I mean, if
Because
you
it gave me a different answer than when you got when I made it negative. Or maybe I just did it wrong.
0
But when I
minus
switched it, I had to make it. I didn't do that though on my paper. But
so you worked it out to this point here?
yeah, but that's I had to. I was like, do I make it negative or positive?
So this should work out.
No, I know that, but that's
So that's
I
after you make
switched
the
it and I didn't take out the negative, but should I have taken out the negative because I switched them?
Yeah.
So that would have given me the answer.
Okay, have a great day, guys.
Thank you.
Yeah,
Pretty much.
Plug in 3 into 3 minus 9, so you have 0. So, okay, your lower bound is 3, so you need to stay at the lower.
Okay. Yeah. But would that put -1 on the top?
Yeah, which is fine.
That's fine?
That's
Oh,
fine.
okay. I didn't know that. Thank you.
So yeah, you didn't check the homework for our row.
Oh, really?
Yeah. I just want to make sure, like.
I'll check it tomorrow.
Okay.
Sorry. Okay. Thank you.
Maybe you lose like everything.
Appreciate it. Thank you. Bye. Thank you.
Yeah, exactly.